In popular culture, black holes are often described as literal empty voids, infinite vacuums roaming the cosmos and actively sucking up the universe. Over a century ago, Albert Einstein proposed that gravity is the physical curvature of spacetime, where any object with mass warps the fabric of the universe around it. Physicist Carl Schwarzschild applied this logic to extremes. He calculated that if mass is compressed into a small enough point, it creates a boundary where the curve of space becomes so steep that even light is trapped forever. This occurs when a massive star exhausts its nuclear fuel. Without the outward pressure of fusion to resist its own weight, the star collapses, crushing its core into an infinitely small point. These invisible distortions of spacetime are the signatures left behind by the collapse of the most massive stars in the universe. Astronomers first confirmed these theories by detecting concentrated blasts of X-ray radiation coming from a source in the constellation Cygnus, known as Cygnus X1. Cygnus X1 orbits a visible companion star, siphoning gas into a superheated accretion disk. Particles in the inner edge whip around at half the speed of light, colliding and heating to millions of degrees, blasting out X-rays detected from Earth. By tracking the orbit of the visible star, researchers calculated that Cygnus X1 is roughly 15 times the mass of our Sun, fitting the theoretical profile of a collapsed stellar corpse. While a 15 solar mass black hole explains a dead star, other regions of the cosmos appear to harbor invisible objects millions or even billions of times larger. Quasars are the brightest objects in the early universe, putting out the energy of 1 trillion suns every second. Chemical or nuclear reactions cannot produce that much power. Only gravity engines on a much larger scale can. To find them, researchers look toward the centers of galaxies, peering through dense cosmic dust at the core of our own Milky Way. Individual stars in the galactic core are whipping around a completely invisible central point at speeds reaching 10 million miles per hour. To hold these stars in such violent orbits, that invisible center must contain the mass of 4 million suns. Farther away, the Andromeda Galaxy harbors an even larger central supermassive, containing the mass of 100 million suns. Current observations suggest these supermassive centers are permanent fixtures, anchoring the core of nearly every galaxy we can see. Supermassives grow by devouring their surroundings. When a star wanders too close, the black hole's gravity creates tidal forces so strong that they stretch and rip the entire star into a stream of glowing matter. A black hole devouring stars one by one takes billions of years to grow. Yet billion solar mass quasars were already active when the universe was only a few 100 million years old. Accretion also has a physical speed limit called the Eddington limit. If a black hole feeds too fast, the radiation pressure from its own accretion disk pushes incoming gas away, effectively choking off its own growth. To reach such immense sizes so early, some primordial gas clouds may have skipped star formation entirely, collapsing directly into massive black hole seeds. These direct collapse seeds provided the mass required for black holes to become the billion solar mass giants that govern the early universe. While black holes are often viewed as destroyers, they live in a symbiotic partnership with the galaxies they inhabit. Galaxies expand by forming new stars out of massive clouds of cold hydrogen gas. When a supermassive black hole is feeding, it liberates enormous amounts of energy. This radiation blasts outward, aggressively heating up the surrounding galactic gas. Because this gas is now too warm to condense under its own weight, the creation of new stars ceases. Black holes act as galactic architects, serving as a thermostat that controls exactly how large a galaxy can grow. For 4 centuries, astronomy relied on capturing electromagnetic energy, like visible light or X-rays, to understand the sky. The LIGO experiment was designed to detect gravitational waves, actual ripples in the fabric of space-time. In 2015, LIGO caught the signature of 2 black holes over 1 billion light-years away. They swirl together hundreds of times a second before merging in a fatal collision. That merger converted the mass of 3 suns into gravitational waves 50 times more powerful than the light output of the entire visible universe. Gravitational waves allow us to perceive the physical vibrations of the cosmos and its invisible builders. If you want to explore more of these galactic mysteries, subscribe and join us for our next journey through space-time.